few minutes more. Yeah, we can wait a few minutes more. Oh, the light. I see.
This is going to be live broadcast online, but is it going to be recorded? Recorded and put online, archived as well?
Broadcasting?
Yeah. But I didn't know it was going to be recorded or not. I don't remember.
It's broadcasting.
It's broadcasted and recorded.
You can tell them if you don't want to.
Yeah.
Yeah, if you have some
it's
secret
okay.
information.
I won't say anything that I don't want to say on record.
You should be polite.
I'm normally very nice. I don't have any enemies. Unlike some of you here.
Oh. Yeah, more people are coming. So, all right, looks like a good portion of people. So let's get started. Good afternoon, everyone. So thanks to the coming to today's colloquium. So we are very happy to have a Professor Sharon Wang from Tsinghua University crossing the street. Sharon obtained her PhD degree from Penn State University in 2016, and afterwards she spent 4 years as a Carnegie Fellow in observatory, and until she came back to Tsinghua as a faculty member in the Department of Astronomy. So she and her group members are focusing on the observational studies of the exoplanet, so mainly using transient and radial velocity method. So she's a project scientist for the next generation precise RB spectrograph CORUS, so for which China is building a big telescope, as well as a science, the team member of the multiple RB technique and observations. So today, she will tell us about a small piece of the never-ending story of the giant planet. So let's welcome Sharon.
Thank you. All right, thanks, Kohei, and thanks for inviting me back again. I was here, I think, a little more than 2 years ago, but I promise what I talk about today is completely different from what I talked about 2 years ago. It mostly focuses on the recent work our group has done since I joined Tsinghua in summer of 2020. All right, this is a pretty powerful laser point. I'm very impressed it actually works. All right, the story focuses on giant planets. I'll start by introducing why we care about giant planets, why in particular we pick giant planet to study. And then I'll tell you 3 interesting stories from our recent studies. That first one, giants are probes of planet formation and evolution. The second one being giant planets as the chemical tracers of the composition of planets, and to that, probing formation and evolution as well. And finally, sort of a question mark was the role of the giant planet in the planetary system, similar like Jupiter and Saturn, and how that could shape our solar system. All right, so we all know that exoplanet discoveries today have revealed to us that there is a great diversity of planets. These are, of course, mostly artist illustrations of the exoplanet discovered today from their temperature, their mass, and radius, right? So those are not real pictures, except for some of the solar system planets listed here. But we can postulate from just the orbital period, mass, and radii of exoplanets that there is a great diversity of planets. And until today, we know over 5,000 extrasolar planets. And not surprisingly, a third of them are giant planets because they're easy to discover, right? And a third of them are what we call super Earths, and a third are Neptune-like planets, and only a small portion is terrestrial planets that are similar to our Earth, not because they're underabundant, but because they're super difficult to find. So we don't know their exact occurrence rate yet. So that's another direction my group is pursuing. But today we're going to focus on this 30% of giant planets Because they're fun, although we've known their existence for over 30 years, this year actually marks sort of the discovery of 30 years of 51 Peg B, the first ever discovered planets around a sun-like star. Because giants are so easy to observe and study in detail, relatively speaking, right? If you compare, for example, Jupiter to our Earth, just to put you sort of in relative scales, give you an idea, Jupiter is roughly 10 times the size of Earth, right? 300 times in mass. And the transit signal is 100 times larger in general, right? It's much easier to detect Jupiter-like planets, gas giants in transit. And the radial velocity, even Jupiter, which has a pretty long orbital period, on order of magnitude, the radial velocity signal, which is the speed of the star, how the speed of a star changes as the gravitational pull of the planets acts on the star, that signal is roughly on the order of 100 times larger. If you bring the orbital period to something smaller, that signal is even much bigger. All right, so even for challenging probes like direct imaging, right? So direct imaging is the next method we're hoping to get through to detect Earth-like planets and also Jupiter-like planets. Even that, for our Jupiter, which has a pretty dim light, that's 10 times brighter than Earth, right? For hotter stuff and young Jupiters, we're discovering those right now, these days, that's orders about 4 or 5 orders magnitude brighter. All right, so for atmospheric characterizations, where you observe either the transmission spectra of the planet or the emission or reflection spectra of the planet, typically the signal is also 1 or 2 orders of magnitude larger. For example, the atmospheric scale height of Earth and Jupiter differ by about factor of 3, even though traditionally Jupiter is not considered to be something that's very easy to characterize, to look through the atmosphere, right? For hot Jupiters that's much puffed up, the atmospheric scale height can be as large as something like 50 or even more. So that's much easier to see through than smaller planets. And that is why JWST is making a lot of groundbreaking discoveries in the compositions of gas giants, because really that's really it's a sweet spot, right? It's very challenging to do small planets, takes a lot of data, but for giant planet with just one simple transit, you can tell a lot. So we like studying giant planets because we can gather their demographics and their composition, and they tell us their formation story as well, or a general story of planet formation. Because if you think about our solar system, right? Our solar system, mostly the major planet in there is Jupiter, right? That's the main gravity perturber, and also Saturn as well. All the other ones are second order perturbations in the solar system. So they actually could dominate the forming history of planets in any system. And we want to know how things really come into shape. That we all know that, you know, stars form from protostellar cloud, they collapse and forming protostars, and then planetary disk and planets forming disks. That's sort of the current consensus. But there are a lot of things in detail that we don't exactly know. For example, this is sort of the famous debate in planet formation, although one of them seems to be winning, as we'll see later, right, is whether planet formation was from bottom up or top down. So in the bottom up story, you have lots of small stuff in the primordial disk with gas and dust, they orbit a young star, right? And small things coagulate and gradually grow into big things, and gas giants are those things that had a massive core that went through runaway gas accretion that accumulated a lot of gas and ended up to be those big giant planets today. That's the bottom-up scenario. And there is also the top-down scenario where you have gravitational instability in the disk. And just like how you form stars in molecular cloud, right, those instabilities would trigger things to collapse into planet directly, right? That's the top-down approach. And so far, both channels work in computers. So if you run your simulation of protoplanetary disk and with some simple assumptions and try to make planets, it's easy enough for both of them to make giant planets. But it's sort of relatively unclear which channel dominates or which channel takes over how much fraction. Until recently, where we have a good sample of giant planets, and one of the major discoveries that sort of points us towards the core equation or the bottom-up scenario is this correlation between the percentage of stars with planets. By then, it was mostly giant planets, and the metallicity of the star. And there is a steep dependence of planet occurrence on the content of metals in the star, which we think also dictates the amount of metals in the protoplanetary disk. So the more metals you have, the easier you would have a core, right? Small solids, and solids coagulates. Maybe it's easier for them to form giant planets. Unlike direct collapse, more or less just disk instability should not depend on metallicity. So this really tells us that maybe core accretion is sort of the dominant model for forming giant planets. However, in the recent 10 years or so, there have been more and more evidence pointing towards disk instability as well, which, by the way, we never gave up. It's just sort of nobody's favorite model except for a small group of people. For example, one of the discoveries, this is relatively recent, is this Jupiter-ish planet at 100 AU from the star, which is really far away, right? So that's the trans-Neptunian area in the solar system. And that's a pretty massive planet. It's direct imaging from HST, ABRB. So how do you form such a massive planet so far away from the star, where you're in the region of the disk, density of dust and gas sort of drops precipitously compared to the inner region of the disk. So it is very hard to coagulate things. But for disk instability or gravitational collapse, it would not be a problem. So distant, massive planets really make us think that, for example, disk instability is an efficient channel, especially for massive things, and especially for a special type of planet that we had doubt about for a long time, which is these giant planets around small stars, or a program called GPASS that our group has been carrying on in the past few years. Those are giant planets, for example, hot Jupiters, around tiny stars that are the M dwarfs that we know, right? So what's special about them? The mass ratio of these are a factor of a few larger than your regular hot Jupiter, of course. And the difficult thing about forming them is that, for example, your star is too small, so it should not have as much material in the disk. So how do you form these things, right? Maybe they form from direct collapse because you just coagulate things more easily. Or if you build them from bottom up, that's just such a struggle in a lot of cases, especially the distant massive ones around M dwarfs. So this is a program that's led by Dr. Tianjun Gan, who just graduated last year. We worked together on many papers for M dwarfs, and we're gonna talk about the most recent 2 papers, sort of trying to tackle the challenge in forming these planets from an observational point of view, trying to distinguish their formation channels. So to be specific, I alluded to the difficulty in forming these planets. Now, what exactly is the struggle? Here is an illustration from one of the papers reporting a discovery of a hot Jupiter around M dwarf. This is a plot showing the gas to dust ratio in a protoplanetary disk. So 100 is, or on this order, is typically what we like to assume. And this is the disk mass to star mass ratio in percentage. And the color marks the total dust mass in the disk, right? So red is 1 Earth mass, yellow is 10 Earth mass. For a typical core of a gas giant, you want on the order of 100 Earth mass or so to trigger runaway gas accretion. And the dotted line is sort of the median and spread in disk mass and dust mass for the star forming region lupus. And this solid line marks the minimal core mass that you would need to form this particular planet that this paper is reporting, and also sort of typical for your trigger for runaway gas accretion to form such planets around small stars. So you can see that for M dwarf in this star forming region, the disk mass is really low, right? Even if you boost the gas to dust ratio, change the gas dust ratio, you can't really boost the total mass of dust by a lot. So if you have to form the core, you sort of have to collect all the dust in the disk, and that's not even enough. So it is really challenging to form these planets. You either have very high efficiency, even that you need very high disk mass, or you just have to have a Euro dust to gas ratio and things like that.
So how do you know the disk mass?
That's a good question.
It depends on the phase.
Yeah. So that's one thing that's highly uncertain. Disk mass alone is a tricky thing, and disk dust mass alone is also a very tricky thing, right? Because you're inferring things from luminosity, essentially. It's just like how you measure galaxies' masses, where you make a lot of assumptions. So I think there are a lot of wiggle rooms there. For example, Liu Yao at Purple Mountain Observatory, he's made some recent measurement, and he can show that disk mass, especially dust mass measurements, can be pretty off. So it's the picture is not that simple. Lupus is just one of the star forming regions, right? There are lots of young stellar associations, and if you plot their disk dust mass, this is 100 times the disk dust mass. This is in solar mass, right? And this is stellar mass. You can see that even for very, very low mass M dwarfs, right, you can have substantial total dust mass, right? And the point is, one of the point is, it has a huge spread, right? For typical M dwarf, for relatively large mass M dwarf, you can have a disk that's basically as heavy as a G dwarf disk, right? So for young stellar regions, this is age, this is dust mass. There is a correlation as a function of age. There is a loose correlation with mass, but really the spread is huge, right? So the struggle, if you think about it, isn't much of a struggle if you want to build these things from bottom up by coagulating the dust and solids in the disk. If you just cut the cusps of these things, right? If you just say, okay, only the most massive disk or most dusty disks would form these planets, that wouldn't be a problem. But the direct implication of this would be that the occurrence rate of these planets would be incredibly rare, right? Because for G dwarf, you don't need, you have enough of disks that have mass that's high enough for you to form these giant planets. But for M dwarf, it's going to be relatively rare. Okay, so all we have to do is to compare the relative occurrence rate of giant planets. For G dwarfs, those should be pretty frequent. And for M dwarfs, those should be pretty hard to form. Okay, let's so yeah.
The total amount of dust mass on the right, M dust is the total amount of dust in the disk.
I believe so.
So then even like super Earth would be difficult to form, right? So if it's like something like one solar mass, sorry, one Earth mass. One Earth mass is like, okay, the whole disk has like one Earth mass.
Yeah, that's why they think this is grossly under. Yeah.
Super Earth.
Yeah.
But then wouldn't this? So they cannot even have like Kepler type, Kepler detected planets around and for most of this, for a large fraction of this. If this is like total amount of dust spread in the whole disk, if you just add the Kepler,
that's right. That's right. The minimal extrasolar nebula has more mass than this, right? In dust.
So, right. So looks pretty problematic.
Yeah. Yeah. Even for regular, forget about giant planets that need those, right?
60,
yeah.
60 Earth mass.
Yeah, I think this is a simple luminosity converted total dust disk mass, and I think they know there's a problem.
If this is like a fair distribution, it imply the fraction of planets like tiny.
But definitely consider the hydrogen, which is not conventional speaking full disks, right? Because benefit something consider the hydrogen consideration.
So these are old. Those are debris disks. Those are debris disks. Yeah, those are gone, right?
What about the 1 megayear?
Yeah, but those ones, yeah. I think that this community is realizing that they're probably underestimating the dust mass because you're looking at the surface emission from a wall, and you're trying to estimate the thickness of the wall. That's my understanding, right? So there are a lot of uncertainty in this. Not done properly. Okay. Yeah. I'm not very surprised that things don't match between this end and the other end. And really also these are young, but We need younger ones too. Yeah. Yeah, but that would be harder. So who knows what happens at even earlier ages. All right, so, okay. So the natural prediction is, okay, you can't still form things, right? Because, you know, everything has a distribution, and distributions have long tails. You're just catching the long tail of things, right? The fact that you're finding these very massive planets is not because that the fact that they don't fall in the distribution is precisely because they're the tail of the distribution, and they should be rare, right? So let's just look at the occurrence rate of, for example, hot Jupiters, which is, again, easy to measure, right? So we began to have second-order statistics like this, occurrence rate of hot Jupiters as a function of stellar type, what we call second-order statistics. And there are lots and lots and lots of literature measuring the occurrence rate of hot Jupiters across stellar type. But really, not until TESS that you're able to measure it across a wider range of stellar bin and really sort of start to bin things. So these 3 points are from TESS. But before TESS, really, you don't know what is the occurrence rate of hot Jupiters around M dwarfs. It is just too uncertain. And from this plot, you can almost fit a power law, but those are upper limits, of course, right? So do you have even more hot Jupiters around M dwarfs, or do you have less? So thanks to TESS, which is this all-sky satellite that scans the sky over the years. It's been 5 years it's running. That's sort of just constantly monitoring a strip of sky. It's because the whole sky coverage is very, very good at finding weird things. So really rare things, right? For example, hot Jupiters around M dwarfs. With this sample, Tianjun and I were able to derive a occurrence rate for hot Jupiters around M dwarfs for the first time. Finally, that this is the quantified result showing that it is sort of an arc, right? It peaks around somewhere K or G, falls off to both ends, although some other recent work calls into question of this. But for M dwarfs, for sure, it is, right, a lot more rare than the hot Jupiters around G dwarfs. And this was quickly confirmed by a similar work done by Brian et al. They calculated the occurrence rate down to even lower mass M dwarfs, and they are consistent with our work, showing that there is sort of this peak distribution of hot Jupiters. You have an easier time forming hot Jupiters around G and K type stars, and really for M dwarfs, they are just hard, right? I think they have some uncertainties in their false positive and candidate validation. So there is some conservative limit. For the things they kicked out, I think they're not truly uncertain. That's my understanding of where the little triangles come from. So at least they are certain about that. You can't fully validate all the things you use in the denominator. Is the problem. Those things are faint, right? Okay. So for hot Jupiters, it seems like there is a factor of 2. Okay, the scatter is pretty large, right? The difference between M and G, say, is about factor of 2 in the occurrence rate, right?
Those are there's a discrepancy
between radial velocity and transit. Yeah. Yeah. That's right. I'll come back to that in a second. And also, this has come from heterogeneous samples from various surveys and mixed stellar types and all that, right? For example, the horizontal error bars mark the range of stellar types. So it's really a mixture. But roughly speaking, right, going from M dwarf to G dwarf, if you're saying, okay, you increase by a factor of 2 the likelihood of having these hot Jupiters, and if you look at your sort of state-of-the-art planet population synthesis model and how much they make Jupiters in their code without considering migration, where you form planets far away and the planets migrate in through whatever mechanism become hot Jupiters, right? Focus on the red curve, which is for giant planets. This is stellar mass. This is the occurrence rate out of their population synthesis model, meaning you grab physics, you do some analytical analysis as well. You're trying to push out a population of planets and see what's their statistical properties. And indeed, from M dwarf to G dwarf, you see a difference, right? It's harder to form giant planets around M dwarfs, easier around G dwarfs, but the difference is a factor of 10. That's pretty dramatic, right? So that made us think, okay, so if the difference in making hot Jupiters and cold Jupiters are different, maybe this is telling you something about the migration efficiency. So this is telling you the differential migration is at work because migration is proportional to planet's mass, but also stellar mass and how the disk mass as well, which could be scaled with stellar mass as well. So maybe this is informing the migration, different in migration histories between these two types of planets.
So here the definition of the cold Jupiter is a Jupiter with a larger semi-major axis.
Yeah, it's just formed beyond ice line. Anything that formed
because the normal place.
So everything beyond, everything was formed beyond ice line because within ice line you don't stick things together.
I also want to figure out the potential bias for RV measured hot Jupiter. So if you focus on hot Jupiter, so RV is actually better, right? Easier, right? I don't know. Basically, no problem to find the hot Jupiter.
No problem.
Gravity.
That's right. Yeah. Transit is also easier because it's a bigger signal, right? So in both radial velocity and transit, there are whopping signals that are huge.
Yeah. Going back to Subo's question, so what causes the discrepancy?
But aren't you on a paper that published in PNAS last year that solved this long-standing issue?
One of the work
towards solving the issue. Yeah, I think it filled in a pretty important missing piece. So what we're talking about, just for the audience, is that the squares are measurements from radial velocity surveys, the occurrence rate of hot Jupiters around these stars, sun-like stars. And the points over here are from transit. You can obviously see that there is a difference, right? So there are explanations for this, and Subo contributed to one of the quantified ones earlier this year. That one of the hypotheses is that, or actually you can quantify and show this could explain it, is that the binary fraction of these two populations are very different. So for radial velocity surveys, you never ever look at binaries. And for transit, it's such a mixture of stellar types. So for some of them, you don't know if they're binaries.
Stellar binary?
Stellar binary.
Oh.
Yeah. So the binarity rate is very different in the parent sample of these two populations. So you're really sort of comparing apples to oranges. So that's one of the explanations which could create trouble. And another explanation, which Subo et al. Showed earlier last year, was that there is also a age difference in the two population as well. And the transit population is actually older than the radial velocity population, because radial velocity, you're sort of looking at the very, very nearby stars that are within the solar neighborhood. Those are your stereotypical disk stars that in population-wise, it's just much younger than the transit parent sample. That could almost fully explain this discrepancy, because hot Jupiters tend to disappear as stars age. That's the major conclusion of the paper, is that, look, hot Jupiter, if you plot hot Jupiter occurrence rate as not a stellar type but age, it's a steady decline. So there, both could explain it, and both could explain it sort of quantitatively. And I think their recent paper did a better job in quantifying that. I think the binary explanation is a relatively minor one. The age one is probably the dominant one. That's my theory, looking at the quantity numbers in your paper, which I'm sure you remember. All right, so this is actually an important point, because next what we're going to do is something that's a little tricky. So now we really want to look at the relative occurrence rate between cold Jupiters and hot Jupiters across stellar type. So this is occurrence rate for either hot Jupiters, the red dots, or the cold Jupiters, the blue dots, right, across stellar type. Okay, so the red ones are from TESS, the same ones that I showed before, but they are uniformly from TESS, right? All the points are from TESS. So unlike the previous round dots, which were sort of heterogeneous sample from all over the place. The blue one is not from transitory, but from radial velocity. But this is the only place where we can get cold Jupiter occurrence rate across a relatively wide range of stellar type. And they are also from one single source, which is the California Legacy Survey. This is a survey that's been running for over 30 years. They were one of the pioneers in discovering exoplanets, so they had the longest baseline in searching for planets. So this is the best catalog ever we have for cold Jupiters. And TESS, really, because it's all sky coverage, is the best catalog we have for hot Jupiters across stellar type. So if you compare the two, and try to do your statistics uniformly, define your mass bins and planet bins, try to do an apples to apples comparison, and then you align the bins and divide them, and we define this number epsilon as the occurrence of hot Jupiters divided by the occurrence of cold Jupiters, their relative occurrence. You arrive at this curve, right? So hot Jupiters, maybe they, in comparison to cold Jupiters, there are more around the smaller mass stars and maybe less towards high mass stars. But this is clearly a very low significant trend, right? So this is just sort of a preliminary demonstration that this is something we should consider, because this is telling you not just the efficiency and speed in forming the planets, but also how fast and efficiently they could migrate inwards and becoming hot Jupiters, and how that changes with the stellar masses. So that's really plans you can do for your planet formation theory. So this is just a proof of concept that we wrote up this paper to sort of bring to people's attention this ratio that we could start using, but really we need more data. For example, at high mass end, and really at more at low mass end, especially for cold Jupiters around M dwarfs. So, but the fun thing about this is that it doesn't take much effort to reproduce this in theory. So that's the fun thing about it, is that if you run your vanilla core accretion formation model there are currently many flavors of core accretion models, and they're grossly divided into two. That one is planetesimal accretion model, where you coagulate bigger things that are like asteroids, bigger planetesimal or even bigger. And one is pebble accretion model, where you coagulate much smaller pebbles, even down to millimeter sizes, right? But under the sort of almost fiducial setting for either models, you try to create cold Jupiters or hot Jupiters around different types of stars with simple disk scaling assumptions and simple migration assumptions. You can sort of reproduce the observed effect. This is, again, stellar mass with occurrence rate. Blue is for cold Jupiter, red is for hot Jupiter, and the brighter colors are the results from the simulation from each model, and the background are the observations. And for planetesimal accretion model, you can tell that it's sort of overproducing hot Jupiters, but for pebble accretion model, it looks like it's underproducing cold Jupiters. But sort of broadly, at least they both match this trend, where you have a peak for hot Jupiter occurrence rate, and for cold Jupiters, it just ever increases as stellar mass, right? And if you divide the two, for the ratio of hot Jupiter and cold Jupiters, both models predicts this declining trend as a function of stellar mass. And really, to the first order, this is just the competing effect of how fast you can form planets vs how fast they migrate vs sort of how your disk mass scales with your stellar mass. So broadly speaking, it looks like what we observe matches the theory of core accretion. So maybe these massive planets around small M dwarfs were formed through core accretion after all. Wouldn't that be sort of fun, because you're sort of testing core accretion to its extreme end and it still works, right? But if you come back to this plot where you think about, okay, so one of the signposts for core accretion is that it really has this deep dependence on metallicity. If you have more metals in your disk, you have more dust and pebbles or planetesimals or whatnot, it's easier to coagulate and form cores and form giant planets. Do we see this for M dwarfs is the big question, right? So this is very preliminary result because Tianjin has a IRTF SPECS program ongoing to systematically observe a bunch of sample of these planets and planet host star to answer this question. But very preliminarily, we can compare the current sample and their measured metallicities and see if there is any trend. So first, if you look at the sample of hot Jupiters and cold Jupiters around G dwarfs, which are these gray histograms over here and the gray background. So the x-axis is metallicity, is the iron abundance, and the y-axis is planet mass, right? And if you plot hot Jupiters and cold Jupiters around G dwarfs, there is really no difference, right? They both prefer high metallicity, as we already knew, right? But if you plot the histogram for the metallicity distribution for hot Jupiters and cold Jupiters around M dwarfs, again, overall, they favor more metal-rich stars, right? But really, for the hot Jupiters, it seems like they favor even more metal-rich stars, even more so than the G-dwarf sample, and especially in comparison with the cold Jupiters. And there is this hypothesis where the cold Jupiter sample in M dwarfs is indeed more massive than the hot Jupiter one. So maybe the cold Jupiters were actually formed through disk instability, and hot Jupiters, those smaller ones that migrated in, maybe they were formed through core accretion. Who knows? So this is very preliminary because, as Zhang Laoshi knows, measuring the metallicity of M dwarfs is incredibly difficult, right? This is why we're trying to do a uniform sample to obtain uniform measurements of these things.
So this is a stellar metallicity.
Yes.
That is not the metallicity in the gas phase.
No, not in the planet. No. It's the star, which we think is the proxy for the protoplanetary disk, and sort of a proxy for the total amount of solids in the disk.
So, but basically, the logic where you try to explain the metallicity dependence, that you have a kind of mass budget for the planet having dust.
Yeah.
So high metallicity might supply more metals, more dust.
Yeah.
So that's why you can easily form the planet.
Yep.
But if we have some discrepancy between stellar metallicity and gas metallicity, so what's going to happen? So
if stellar metallicity does not represent the disk metallicity, then all of these assumptions broke, right?
Yeah.
Exactly. What do you do? That's a great question. I don't think we're ready to accept that truth, to be honest. But I think one day we have to face it, right? But I think the basic assumption is that even if they're different, the difference is probably small. The complication, the major complication, does not lie in the fact that stellar metallicity is different from disk metallicity. It is in the fact that disk is a very complex thing that is highly stratified in terms of its state of matter, chemical composition, temperature pressure profile, magnetic field, right? So different locations of the disk and the different disks would have very different properties. And that's sort of the zeroth order challenge we're facing in drafting these models. Yeah. Which brings me to the next topic, which is, can we link the building blocks of stars to planets, right? So we were sort of inferring by looking at ensemble of planets, their occurrence rate, and whether metal-rich stars tend to have certain type of planet or not, to try to link back to the formation of gas giants. So now let's look into the detailed composition of gas giants in their atmosphere. So atmospheric measurements of in situ abundance in the gas giant planet, and their link to things like stellar properties and planetary properties, and see if there is any link. So there is this very interesting trend in the solar system that is linking the methane abundance, which is this orange line, with planet mass, right? we want to measure the chemical abundance of planets in our solar system, but it turns out it is very hard, right? If you think about it, how do you measure the metallicity of our solar system planet, right? You cannot observe transmission spectroscopy, right? You either observe their reflected light, or you send probes to measure the abundance in situ, right? So it turns out the best measured abundance for solar system gas giants is methane, because methane is just everywhere in those cold gas giants envelopes. And there is this interesting trend where it's sort of a tight correlation between methane abundance in them and their planet mass. Methane, relatively speaking to hydrogen, is a pretty heavy thing, right? So your traditional gas giants has very tenuous, low-density hydrogen helium envelope. As you move to smaller planets, you have more and more metals. So it's not very surprising that you have this trend where more massive planets would have a lower metallicity, right? Because they have gaseous envelope. As you have more massive core, you create more gaseous envelope, which sort of dilutes your overall metallicity, right? So this is for solar system. So of course, we wonder if a similar trend exists for extrasolar planets. So in 2009, Louis Wellbanks collected all the HST data back then and measured the water abundance in a group of gas giant planets. Some are even down to the super Earth regime, and try to see if there is a correlation between water abundance, because you can't really measure methane in those planets. They're pretty hot, in the water abundance and their mass. And he found sort of a tentative trend, right, in water. And in sodium and potassium, which are two other elements you can measure with HST, it's just a mixture of story. But the picture is very messy because those planets do not live in the same system, right? So when you measure their water abundance, which was used as a proxy for oxygen abundance, you have to consider their host stars actually have different oxygen abundances, right? So they were not normalizing the water abundance of each planet against their disk oxygen abundance. Maybe some disks would have more oxygen and some would have less. So the proper thing to do is really, you should normalize these points against the stellar abundance. So that's what we did. We tried to clean up the data. By looking at the graph, you can already tell the correlation is very weak, although it seems like it's parallel to the solar correlation. Wouldn't that be nice, right? But really, the correlation is already weak. Plus, there is some additional scatter introduced by not normalizing against each stellar abundance, right? It's just planets. It's such a heterogeneous sample, and there are some wrong measurements in there as well. So if you clean this up even further and correct each point by their stellar abundance, and redo your statistical analysis carefully with a very good sample, kick out the bad apples like K218b, which doesn't even have water. We know that by now, but we didn't know that 5 years ago. And do your statistical test, you can really tell there is no correlation, right? It's a very weak correlation. First of all, the correction, unfortunately, is not very big, but fortunately, it's not very big, right? But second of all, if you correct all of them, and then kick out the bad apples and redo your statistical analysis, is really a 2 sigma correlation. So almost no correlation. So that's discovery number 1. And point number 2 is that we're soon going to find out the true answer for whether there is a correlation or not, because if you put the most recent JWST water abundance measurements on top of it, unfortunately, there are only 2 by now. I think there are more for the small, especially for the smaller planets. But by the time we finished writing the paper, there were 2, and they don't really corroborate with your story, especially this is the same planet, WASP 390, right? And for JWST measurement, it's going to be even more important to do your stellar abundance measurement properly, because the error bars are so tiny, right? You're really going to start to see if there is a real trend or not, and what's the true inter-system variation of this. So this is the work done by a postdoc working in my group, Dr. Tsinghua. She's working on this correlation between the planetary properties, not just mass and other things, and planetary atmospheric abundance. And for water, this is what I just introduced, right? It's basically just nothing, right? For sodium and potassium, it's a flat line as well. We're going to do some preliminary study to see if we can sort this out with more CSST observations, which you can see sodium and potassium emission lines, unlike with JWST. So this is highly complementary to JWST observations. And we're also going to try with JWST as well, but not with inter-system correlations, because those planets are all over the place. They're from different systems. They have very different formation history, and they were formed under very different environments. So what we really want to do next is to probe the intra-system uniformity, right?
So quick question. So what's the chance of measuring planets for these planets?
For those ones,
yes.
Those particular, that's not very promising because of this plot. So this is equilibrium temperature of planets, and this is planetary mass. All the orange points are the ones that are going to be observed by JWST. For hot planets, the major carbon barrier is CO. You have to really move down to what we call warm Jupiters. Well, there's a loose definition of it. It's around 1,000 Kelvin also, right? So all those ones I showed were hot Jupiters. So you're not going to see methane. So there is a push for measuring more warm Jupiters with JWST right now. So we're going to see more methane discoveries.
What about water for our
that's my second point. All right, which is the last thing I'm going to talk about. I like those questions, so I think I'm going to cut the last part of this talk and just focus on this. So the next thing we're going to do is to use pairs of giants as probes of intrasystem uniformity, but also chemical compositions of planets and linking back to their formation, and in particular, warm giants. This is because of this plot again, right? And by warm giant, we really mean, oops, wrong plot. Things in this temperature range, right? It's hot enough that you don't form water cloud. So you see water, which is the major oxygen barrier. And you see methane as well. That's your carbon carrier. And you also see this very precious thing called ammonia. If you're hotter than about 600 Kelvin also, nitrogen is going to be locked in nitrogen gas, right? So you want to observe ammonia so you can measure your nitrogen. So with pairs of giants in this particular temperature range, especially this precious target, we pick it out. We're going to try with JWST, hopefully this cycle, next cycle, cycle 4. You can constrain its atmospheric composition with three carriers, carbon, oxygen, and nitrogen, all three of them, right? And by measuring the ratios between carbon, oxygen, and nitrogen, you can sort of infer their formation location, because depending on your snow line, right, especially nitrogen has this is formation location in the disk, and those are sort of different formation scenarios. So depending on where your giant planets were formed, you're gonna accrete different kind of things. For example, if nitrogen snow line is here, you're formed beyond the nitrogen snow line. Nitrogen is gonna be locked in ice, so that's solid, right? And here is gas, right? So your atmospheric metallicity would be different depending on where you form, right? So darker colors means higher metallicity because you're gonna accrete more icy pebbles into your atmosphere. And the bluer colors means you have more solid, and here you have more gas, you have diluted atmosphere. So especially nitrogen, which has only one snow line, unlike carbon, which has multiple snow lines, having both C and O, you're gonna be very sensitive in probing the formation location of these things, more so than what we currently have, right? So pairs of giants are very interesting because depending on their measured metallicity in their atmospheres, maybe they could be traced back to different formation locations because of those snow lines. So that's our next direction. And before we go, I just wanna pitch for this idea for pairs of giants as well. So not only do you add more points to that plot, you're sort of measuring the relative abundance. You can measure the relative abundance in the giant planets in the same system more precisely, right? So you can really compare apples to apples on the same plot where you pull the solar system planets, which were formed in the same disk, right, on the same line, right? So we really need more multi-giant planet systems be measured and put on this line as well. And pairs of giants have their own charm as well. This is the last thing I want to show. Bear with me for a few more minutes. If you plot all the transiting pairs of gas giants, or more than pairs, so planetary systems with 2 or more gas giants that transit, right? And you sort them by the period of the innermost gas giants. You put them on this log orbital period plot. This is their host star. The color is just the brightness of the star, and the size scales with the size of the star. And the planets are scaled according to their size. The color scales with their mass. You can see a very interesting pattern, which is that pairs of giants have sort of a favorite distance, right? They really come in pair and it's close to each other. It's a constant distance in a log plot, which means it's a constant period ratio, right? The ratio is the same. All right, here is a quick zoom in plot. I like staring at this plot because it's so pretty, and more importantly, ChatGPT made it. It's very good at making pretty plots. So that's the transit sample. So really, there are a lot of TESS discoveries and lots of Kepler discoveries as well, sort of which brought us to this critical sample of over 40, almost 50. If you look at the radial velocity sample as well, so all of the sample mixed transit or radial velocity, this pattern sort of persists. Oops. So there is still this preference of equal distance between pair of giants. If you plot the distribution of period ratios of giant planets, 177 of all of them, you see a clear peak near 2:1 period ratio, right? And this is very different from the small planet found by Kepler. So those are the super-Earths and sub-Neptunes, their period ratio distribution as found by Kepler. Their peak is 3:2, to the right of 3:2, right? A giant planet has a peak near 3:2 as well, but not as prominent as the 2:1. And the Kepler small planet has a weak peak at 2:1. It's way more spread out to the right of 2:1, unlike the giants, right? Jupiter, Saturn is over here. So the leading theory of this, explaining this, is that they experienced convergent migration, where for whatever reason, either the inner one waited for the outer one to catch up, or the outer one caught up with the inner one, and they were locked into 2:1 resonance, which is a much deeper resonance for the giant planet than the small planet. The small planets can be kicked out relatively easily out of resonance, and to the right, preferentially because of dynamic scattering, breaking up the resonance chain. But 3:2 resonance is a deeper resonance for the small planets, so they're stuck here. But the giant planets, because they're so massive, once they're stuck forever. They're going to just go migrate together in a 2:1 resonance configuration. So 2:1 resonance systems probably went through migration. We know for sure, which is really precious. And there are 2 of them in the same system, so you can probe their planetary atmosphere properties in a differential way, right? So that's our ongoing program with Gemini right now, to measure the masses of several of them, because some of them don't have masses. If you don't know the mass, you don't know the surface gravity, you can't constrain your atmosphere very well. So that's the first step. And then we're also going to go for future JWST programs to measure their atmosphere. So that's sort of our next plan, in addition to seeing how giants influencing the properties of inner planets, which I'll skip today. If you're interested, we can talk about them later. So to summarize, since I'm at time, right? we can use giants as probes of formation and evolution because we really, 30 years after the start of exoplanet, we've accumulated so much data to study them in details in second-order statistics or even in third-order statistics, like the ratio between different occurrence rates, right? And they are also really great as chemical tracers for their atmosphere formation and linking back to their host stars, and especially pairs of giants, I think presents a unique opportunity for future breakthroughs. So that's the direction we're going to push. And with Magellan TESS survey, we're trying to answer the question of how gas giants would influence the inner planets, like how Jupiter has shepherded the inner solar system planets, protecting them from being bombarded and maybe strangulated them a little bit so they're so small. Who knows? All right. So that's the science I want to talk about today. But before we go, as I mentioned, as Kohei mentioned in my introduction, I'm the project scientist for this spectrograph called the Canary Hybrid Optical High Resolution Ultra Stable Spectrograph, CHORUS. We're building it for the 10.4 meter telescope GTC in Spain on the island of La Palma. We hope to deliver it in 2028. This is an instrument that everybody could use once it's delivered to GTC, because we're going to get partnership with GTC to exchange for 10% of time. So if you're interested in doing science with this, please talk to me. We're finalizing the science requirements and the design of the spectrograph to make sure we can do the core science. And also, if you're interested in spectroscopy in general, especially high-resolution spectroscopy, we're going to continue this thing that we had last summer in Yunnan, that Yuan Haibo and Xiang Maoshen organized, the ABDAC workshop, the Astro Big Data Exploration Camp. Last time it was on photometry and low-resolution spectra. This year we're going to do mid-resolution spectra and high-resolution spectra, especially teaching the grad students and postdocs and even senior undergrads how to do high-resolution spectroscopy, extracting information from spectra. I have to say, escaping the really hot Beijing in early July to Kunming is a brilliant idea, not to mention that it's the season for wild mushrooms, so it's double delicious. All right, with that, that's all for my talk. This is a summary slide for what we do in my group, which is called Exo Lab, and thank you for listening.
Yeah, thanks, Sharon, for a very nice talk. Okay, it's question time.
So could you go back to the slide that shows the water, potassium, sodium abundances in?
Yeah, the scatter plot.
Yeah, right. And the plot about before it, and well, this also works. So basically, these are observed from the transmission spectrum of this Jupiter size or sub-Jupiter size exoplanet, right?
Yeah.
So I have been primarily doing some Earth-like planets, so I'm pretty much a rookie for Jupiter-sized planet. But still, I've got a question: why do people think that the abundance of water is kind of related to the planet mass instead of related to the host star's properties? Because it seems to me that in the gas phase, the formation of water starts from the ionization of molecular hydrogen. And that's a speed determining step of everything. That's question one. And question two is like, well, I mean, we know that in the solar neighborhood, the abundance of sodium is 1 order magnitude higher than potassium. As you can see here, the gas phase sodium is 1 order magnitude less abundant than potassium in comparison. I think people have been trying to identify similar type of things for planetary disks. There are some types of explanations. Do people in this kind of Jupiter-sized planet community have a good explanation to this phenomenon, or not?
Okay, you have two questions.
Yes.
One is, why do we plot it against planet mass? Because in your opinion, this is not the first thing you would think there is a correlation. I think the quick answer is really, it was rooted back to the solar system correlation of method. It's really, we don't know what's a good correlator to correlate, honestly, because there's currently no correlation in atmospheric properties with anything, right? There seems to be like a sequence of cloudiness, but now I think with GLIC that gets more and more complicated. So that's the answer to that question. But if you have better suggestions, we'll be more than happy to try. So Tsinghua tried other axis values like period or whatever, right? For this sample, this is not the best place to test because the water measurement is so uncertain, right? But we should talk and see what's the most appropriate thing. Stellar effective temperature, I don't know, total UV emission, or whatever, right? Yeah. So your second question, which I didn't get, and I probably am not the correct person to ask, is the sodium and potassium abundance in planets and how that correlates to their existence in disks.
Yes, because this kind of inversion in the relative abundance also I think that also occur in disks. So yeah, because it is there. I'm just curious whether the planet community is having an answer to it, but it seems no, not yet.
I know too little to be definitively answering your question to be no, we didn't. But I really don't think we thought very hard about it. I think the current thing that sort of boggles our mind, or their mind really, because I'm not an atmospheric person yet, right?
Anyway.
People like Tsinghua or Yanfei, right? What bothers them the most is that, okay, we're measuring this sodium and potassium.
Not
see
a bad
this
news.
whooping emission line, right?
Yeah.
Like, what does that tell us about their abundance in the atmosphere and their line shapes, inferring things like the dynamics of the atmosphere, right? And for some of the cases, you see something, the line is so narrow, right? You're not even sure if you're seeing things or not. So that's it. We should talk, because I think linking...
Not a bad news, because we really got something to do.
Yeah, linking heavy metal elemental abundance to planetary properties is a very tricky thing.
I understand.
So for the longest time, the x-axis in a different plot, linking elemental abundance to planet properties, is the condensation temperature for these metals, which I think is just absolutely absurd, because which metal exists in atomic state in the disk, right?
I totally agree.
So the x-axis, so that's another direction we're trying to do with Huiling and Zhang Lao's group and Wang at NOC is, we should measure these abundances more precisely in both stars and planets, and B, condensation temperature is definitely not the right correlator to use.
Yeah, we can chat about the physical picture that I want to propose after this talk. I'll leave it.
I really don't know this that much. Yeah, that's a sort of a sidetrack.
Yeah, that's a wonderful discussion. So, what questions?
I think the core equation prediction for the cold Jupiter frequency around 0.6 solar mass star, the thing will show like a couple percent, is almost certainly already ruled out by the microlensing result, where the cold Jupiter frequency is much higher, and the average stellar mass for microlensing hosts is around 0.5 or 0.6 solar mass. I'll be very surprised that if most of these microlensing cold Jupiter has a host much greater than this. But anyway, my question is really for this for the California Legacy survey. It looks like the big error bar for this is due to the small sample of M dwarf.
Yes.
And is there any prospect to increase this?
Yes. So the near
significantly?
So the near infrared spectrographs is sort of finishing their first generation surveys of M dwarfs. I think hopefully soon, at least from HPF on HET, they're gonna release catalog of better occurrence rates for things around M dwarfs.
What's the sample size in the California Legacy?
I don't think it's more than 10. That's what I recall.
Oh, okay, that's very small.
It's very small because they're grossly magnitude limited, and there is only so much M dwarfs brighter than
this new survey, what's the sample size would be?
For HPF, the parent sample is probably on the order of 50. Oh, you're like,
still,
50.
Still
well, compared to microlensing, I think we're pretty miserable, right? But that's a good point, right? Microlensing is really finding a lot of cold Jupiters that they are all presumably M dwarfs.
The second planet by microlensing is a cold Jupiter of 4 Jupiter mass around 0.6 solar mass star.
Yeah.
So that's confirmed by like we figure out the mass from HST, and now recently confirmed by TESS.
Yeah.
And then in the near future, we'll figure out all the host, more host masses
with parallax
to pin down like exactly this. The host, because now statistically you can say host mass is like 0.5.
Yeah.
Around 0.5.
Yeah.
Okay, there's a range.
Yeah.
But I think that point is
already off.
I think it's almost certainly ruled out. But anyway, this is problematic. This point is, I don't think it's consistent with microenvironment.
Yes, order of magnitude off.
Yes.
Yeah. Yeah, I have to ask. So Kangrou Guo, who's a postdoc fellow at TDLI, ran these simulations. Although this is more or less the Fujosho model, she still had to tune things. So
yes.
maybe
it's a long-standing problem with
for co-creation
because their
as
prediction is like this.
Yeah. Definitely more work to do for M-dwarf giant planets. Yeah.
Right.
That's a good point.
No more from back.
So, naive question from a person who doesn't work on this. So again, following Lila's question on this water abundance versus planet mass plot, I wonder what if you overplot the solar system planets?
I forgot to answer one of the questions he raised in the middle.
Yeah.
How about measuring water abundance for our solar system planets? And Lila is laughing. This is one of the most intriguing thing about using GWST to measure exoplanet atmosphere. We're gonna measure the water abundance more precisely for extrasolar planets than our own solar system gas giants by 2 orders of magnitude.
Okay, why so?
Because all of our solar system gas giants are so cold. Water condenses into clouds, right? It is very hard to probe the atmosphere of our solar system gas giants, in fact, right? They have multiple layers of clouds, and water is way down there, right? Even if you throw things into there, which we did with Jupiter, the error bar on water abundance is still larger than the error bars here, which is cutting across the entire plot. Let me see if I have that plot. I think it's about 2 or 3 order magnitude. At least we can do better in situ measurements, right? Yeah. But the problem with in situ measurement is that you're probing a single line of sight. So a lot of the abundance of Jupiter comes from that one line of sight dropping things into there, right? So
all those probes sent to the external planets within a solar system are actually trying to probe the water in some other places.
In other phases, yeah.
What about Jupiter's moon? So you can go into the Jupiter's moon and also
yeah, we have planned to go to Saturn's moon, for example, right? But then you're talking about a different measurement. But no, because something that went through runaway gas accretion and had thick gaseous envelope, the interaction of those massive bodies would be very different than, say, even a sub-Neptune. For example, the paper which I was projecting, it was JWC measurement on a 2 or 3DI sub-Neptune. So for things that did not go through runaway gas accretion, the envelope gas fraction is very different. And for some of them, for example, they lost their primordial envelope already, and their second generation atmosphere composition highly dependent on interactions between things like magma ocean on the surface, interior composition, and delivery of icy pebbles to form there. So it's a completely different formation story. So even if you measure the Jupiter's moons like a Ganymede, right? Ganymede is like a Earth, right? It's almost Earth size, right? That's not gonna help you solve Jupiter's problem. Yeah, I know, right? What do you think? PAH? Oh, wow.
really.
Yeah.
I mean, transmission spectrum that you something that you propose that would be a particular speed.
Yeah.
Because of the need to find the level to a skeleton go vibrational, vibration, just vibration. See whether that is a super
Another naive thing. So you guys just mentioned the other phases of water, like liquids and ice water. I know as a common sense that in ice water, in liquid water or ice water, methane and water are always correlated. So I wonder if this is loosely in any way related. I mean, methane and water. It's a greenhouse gas, right? It's always water soluble. Okay. Okay.
At the bottom, at the bottom of the ocean.
Okay.
That's pretty uncommon.
Okay.
At this moment, we can't expect. I know people have been proposing that we can get some more methane from the bottom of the ocean, from the other planets in our solar system, but it's not part of the story for this movie.
Oh, okay.
It's a creativity.
Yeah.
All right. Thanks.
Yeah, thank you. I think it's a good time for me to pick up my daughter from kindergarten.
Yeah.
Sorry about that. So if you have more questions, oh, by the way, so let's thank the Sharon again first. So very nice talk. And if you have more questions, so we have a dinner from 6 p.m. in the restaurant just outside the campus, the West Gate. And so if you join, so we have maybe 2 more seats available. So please join if you want to talk to Sharon about the science or something. And also we can meet at the gate of this building, so 5:30. So we go there by walking.
One more.
Sure. 5:30 here. Okay.
All right.
Yeah,
Thanks, everyone.
Yeah, thank you.